Okay. Does it look like it's working?
It's gone.
Okay. All right, so today's going to be kind of screwed up because I got kids that are gone, and then I think the May South people are going to be having to head out for pep assembly. So this is why I'm going to record this. And then what I'll do is, this is actually the first time I've ever had to do this with you guys, because you guys have always been here. So this is cool, okay? I appreciate that. So what I'll do is, I'll upload the videos, and then I'll merge them all together into one big video, post it out on YouTube. So if you're ever gone, we never had this discussion, which is cool. So, but if you're ever gone, then email me, say, hey, work out, record the video. I'll figure that out if you're not here, probably. And then that's what I'll do. And then I'll just send you that link to that video. And that's how that'll work. And if there's any like documents or anything and you're gone, I'll send those as an attachment. I hate Google Classroom with a passion, and I refuse to use it, but that's a whole nother story. Okay, just because.
You use Blackboard?
No.
Good, because that's even worse.
That was the
No.
worst.
So what I've just got my own system, and so I've got everything stored in my own system. So I just send it out to you as an email, because that's easier than trying to push the system train wreck. So anyway. That's just me. And conveniently, I've been here long enough, and I'm an old dinosaur, and they just let me do my own thing. And it's good. So, because I hate Google Classroom. Anyway. All right, so let's chit chat. So yesterday we started talking about 4 fundamental forces. And these are the 2 that dominate your life. Okay? Your day-to-day existence. Of the 4 fundamental forces, obviously one is gravity. Okay? Which is kind of cool. Without that, we wouldn't be here. And the other one is the electromagnetic. Now, this is the one that is, we talked about yesterday. This is the most diverse, okay? It creates light, okay? And we're talking about this in lab today. It's what creates friction. It's what holds your particles together that make you up. It's what allows us to have electricity. It's what allows us to have your cell phones that work, okay? Because if the universe was created, and again, this is one of the great mysteries, is that if the universe was created and nothing had charge, okay, like everything was just neutral, like basically the universe just created neutrons, we wouldn't be here, okay? And one of the great mysteries also, and they think these small particles called quarks, which we'll get into later, might be a key to this, but when the universe was created, what should have happened is like if you take the square root of 4, what's the square root of 4? 2 or minus 2, right? So what should have happened when the universe was created, the universe should have created equal amounts of matter and antimatter. So it's kind of like the square root of 2 plus or minus 2. But the cool thing about antimatter and matter is when antimatter and matter run into each other, they annihilate each other, and it turns back into pure energy, okay? And that's from Einstein's equation, E equals mc squared. And so if the universe had always created equal amounts of matter and antimatter, we wouldn't be here talking, because that matter and antimatter would always be running into each other, and they would just annihilate each other. But something shifted, and we don't know what. But something shifted, and we created a little bit more matter than we did antimatter. So what we consider matter, okay, hey, electrons have negatively charged, protons have positively charged. If it was antimatter, electrons have positively charged, and protons are negatively charged particles. So something shifted in that cosmic beginning that we ended up creating more matter than we did antimatter, because if there were equal amounts, the universe would just continuously annihilate itself, and we wouldn't be here. And so, probably when in doubt, if I say, hey, what's the fundamental force that causes friction, or light, or anything? It's probably the electromagnetic force. It's what keeps you from being sucked into the center of the Earth by gravity, okay? But like I said, it's cool, though, because it holds it together, but yet it keeps things apart. Evan?
Are we going to talk about the weak and strong nuclear force at all?
That's what I'm getting into next. Okay, so which is actually the next segue. So, Evan brings up the strong nuclear force. So this is where you have to have a little bit of a historical background. So after J.J. Thomson discovered the electron, okay, and that's what I showed you yesterday with the cathode ray tube, okay? So Thomson discovered the electron. It's like, oh man, now we're back to the drawing board, because the physicists were all happy because they're going, great, we now have a job. Because they thought, oh man, you know, we're out of a job. We found matter, we found gravity. What do we do now? You know, it's just like, how do we justify our existence if there's nothing new to discover? We found out everything. And so when Thomson found the electron, that created this whole cascade of events. And they were still holding on to the idea that matter and atoms were these like tiny little Lego blocks. And the plum pudding model was cool because no matter what the model was, you had to explain the stability of atoms. So, for example, I've had this table, okay, I got this table new in the fall of 1994. Okay, this is how long I've been teaching behind this table, since the fall of 1994. Michael just shakes his head and goes, wow, okay, old. So there's a lot of things that I worry about when I walk in my room every morning, okay? One of them is this table that turned into a squirrel, okay? This table is going to be a table. I don't worry about that, okay? The tables are going to be tables. It isn't like I'm going to walk in like half my table has decayed into something else, okay? And it's like different, okay? It's a table. It's going to be a table. So atoms are incredibly stable. So what they came up with when Thomson came up with the negatively charged particles, so they imagined this chunk of Lego called an atom, where you had an even distribution of these positive and negative charges. So it was called the plum pudding model. Okay, keep in mind all this research was done at Cambridge University in England. Okay, so that was like the leading research facility. And so they were British. They said, "Yeah, it's the plum pudding model. Everybody, we'll have some tea, crumpets, and a bit of plum pudding." Okay, and it was kind of cool, and it worked. Okay, because it was stable. Okay, you had this even distribution. It was cool. Now, along comes Ernest Rutherford. Now, you need to put physics in perspective comparative to other sciences. All of the people that were doing this research were physicists, okay? The chemists were trying to figure out how to make a more efficient way to make cocaine, okay? That's a true story, okay? Or synthesize drugs and do something, okay? Ironically, it's the chemistry department that talks about the structure of the atom, but it was physicists who actually figured this out. So what Ernest Rutherford did is that he took a radioactive source like plutonium-238, and that was in this box, and there was an opening in this box. And he didn't know what the particles were. He called them alpha particles. It turns out that they were a helium nucleus with the 2 electrons stripped off. We didn't know what they were at the time. We hadn't discovered the element helium at the time. We knew there was these little bits of matter. And everybody has this perception that they were like, you could actually see these particles bouncing out, okay? You can't see these particles. They're the nucleus of a helium atom. But he was clever. And what he did is that he put up this phosphorescent screen. And whenever these particles would hit this phosphorescent screen, they would excite the electrons in that phosphorescent screen, and they would create a flash of light. Okay, so that's how we even knew that these particles were being emitted, because they would hit this phosphorescent screen and create a flash of light. And so what he did is that, kind of like what I did yesterday with the balloons, where you had positive and negatively charged particles. So what he did is he basically, in a crude version, he put a negatively charged balloon beside the path that the particles were taking. And he figured out that these particles were deflected up towards the negative balloon. Ah, okay, right. So these particles, since they're attracted towards like the negatively charged balloon, these particles then have to be positively charged. Because if they were positively charged, if they were negatively charged and they got them near the balloon, what would they do? Yeah, they'd be deflected away. But since they were positively charged, he would notice that this path would curve up a little bit. Okay, cool. So now he knew that the particles that were being kicked out had a positive charge. Okay, and that's going to be a key part of the story. They had a positive charge. Then he says, okay, hey, I'm going to take some gold foil. Now the cool thing about gold foil is that gold has a very, very unique ability to hold its atoms together. And then gold foil is literally like one layer of gold atoms thick, okay? It's incredibly, incredibly thin. And to the naked eye, it appears solid. So like, even though it was one atom thick, you could not see through the gold foil. So if I held it up, like I couldn't see Cassidy if I held it up, okay? But it's really, really thin. So he puts this sheet of gold foil in between the radioactive source and the phosphorescent screen. So here's the great analogy that you talk about how physicists approach this problem. Okay, physicists at the end of the day, we like to bounce stuff off. We like to break stuff. We like to smash things together. That's kind of what we do. It's our gig, okay? If you like green slimy stuff, go to biology. If you like stuff that smells bad, go to the chemistry department. If you like to smash stuff together, hang out in the physics department. Because here's the great story. You give a Volkswagen Bug to a physicist and you go, hey, what's made up, what constitutes the Volkswagen Bug? What are the parts of a Volkswagen Bug? He says, I don't know. Look, there's a brick wall. Let's smash the Volkswagen Bug into the brick wall. Cool, okay? So he gets the Volkswagen Bug up to about 15 miles an hour. He smashes it into the brick wall and he goes, oh, look, there's a little bit of a bumper that fell off. Okay, so there's a bumper that makes up the Volkswagen Bug. Well, 15 miles per hour is good. 150 miles per hour would be better. So then he gets it up to like 150 miles an hour, smashes it into the brick wall. Oh, look, there's a mirror and glass. Okay, now we know more of what made it the Volkswagen Bug. So let's get this thing up to like the speed of sound, about 700 miles an hour, smashed into. Oh, look, there's an engine inside of that thing. Okay, what's the engine made of? I don't know. So let's get the engine up to about, I don't know, maybe 3,000 miles per hour. And then we're going to smash that against another engine. That'll be cool. Let's smash the engines together. Okay, wow, look, there's pistons inside of the engine. That's cool. What are the pistons made of? I don't know. Let's smash them together. And so that's the process that physicists go through. And that's what happens with particle accelerators. Okay, like there's any number. There's one in Chicago, there's one over like Switzerland and France border called CERN. And basically that's the mindset of physicists. So it's like, what are protons made of? I don't know. Let's smash them together and see what happens. It's kind of cool, right? What are electrons made of? I don't know. Let's smash them together. So this was his mindset. He goes, let's smash stuff into the gold foil and see what happens. So what he found, does anybody remember what the results were from the gold foil experiment? Evan.
Didn't most of them go through and deflect just like a little bit?
Yeah. So it would be like me. That's exactly it. So it would be like me taking this golf ball and throwing it at that wall, and the wall appears solid, right? Now the golf ball bounces back, but what Rutherford did this with gold foil, it actually went straight through. So it would be like me throwing this golf ball at that wall, and it actually shows up on the other side.
You hit someone.
Huh? Well, it hits the phosphorescent screen on the other side. Now, every once in a while, they would get deflected, okay? Just a little bit. Every once in a while, they'd be deflected even more. And every once in a great while, literally about 1 in a million, what it would do, it would hit the gold foil, and it would bounce back. So then they would see that flash of light behind them, okay? And how they kept track of it is that he had his graduate assistants. It was a horrible job. He had graduate assistants sitting in this dark room with a piece of paper making tick marks on a sheet of paper where they saw the flashes of light. And about 1 in a million, it would hit and it would bounce back. Very, very rare. And this is important. It was very, very rare. Most of the time, these particles went straight through. So Rutherford out of that had two big things. He concluded that most of the atom was actually empty space. Even though it appears to us to be solid, in reality, it's mostly empty space. So it's somewhat analogous to like a fan. So if you see a fan blade spinning, it looks solid. But in reality, there's just 3 individual blades that are spinning. But they're spinning so fast that it appears to be solid. So that's what he figured out first. Okay, most of the atom is empty space. The nucleus, though, because that positively charged particle hit it and bounced back, he concluded that the nucleus was very, very small and positively charged. Now, this created a huge problem, okay? This literally, it shook physicists to the core. Because if you saw what I did yesterday, okay, remember when I charged both balloons and I tried to push them together, what did it do? Yeah, pushed them apart. They wanted nothing to do with each other. They had nothing to do with each other. Now, the analogy that I'm going to tell you, I can say because I grew up with 3 older sisters, okay? So let's say that you have 6 girls that don't like each other, okay? Somebody said something about Snapchat, Twitter, I don't know, okay? They don't like each other, and they're still holding a grudge, okay? From like 7th grade. Like, if you see each other walking down the hall, like, they will like go down opposite halls just to avoid being in the same hallway, okay? They don't like each other, right? So this is what happens with protons, okay? Protons don't like each other. Why?
Same charge.
They have the same charge, right? You try to put 2 protons together, they're going to be going, screw you. I know what you said to me about in 7th grade. Okay, no, get away from me. Okay, they're still carrying this grudge, even from the beginnings of the universe. Okay, these protons have been around since the beginning of the universe. They still don't like each other. They're still carrying this grudge. But, if you take those same 6 girls who hate each other, but if you confine them into a very, very small space, like let's say you put them into a Volkswagen Bug, okay? You take all 6 girls and you force them into a Volkswagen Bug. They're going, I don't want to go, I don't want to get journalists, okay? And you force them into it. At that point, they become the best of friends. They're taking selfies, they're, braiding each other's hairs like, oh, my BFF. I mean, they're the best of friends, okay? They're the absolute best of friends, okay? And there's this incredibly strong bond that hold them together. But only if they're inside the Volkswagen Bug. Because if you get them outside the Volkswagen Bug again, guess what? They don't like each other. So this is what happens with protons. So protons don't like each other. And this is what they had to explain. It's like, there has to be a force stronger than the natural repulsion caused by both, because they're positively charged. Okay? So this is where they introduced, and they came up with a very clever name called the strong nuclear force. Oh, okay. Because, hey, it's true. So it's the, by the way, if I ever ask you, what's the strongest force? Do not overthink this. Don't tell me gravity. Gravity is actually the weakest of the forces. It's the strong nuclear force. Okay, if I ever ask you that question, what's the strongest force? Don't miss the question. It's the strong nuclear force. So, but it acts over the shortest distance. Okay, so it isn't like I can put 2 protons like here, and all of a sudden, boom, they're going to form a nucleus. Okay, you have to get them incredibly, incredibly close for the strong nuclear force to take over. Now, forces are typically carried by particles, okay? What we call force carriers. Like the electromagnetic force is actually carried by photons, okay? So like when I was pushing those 2 balloons together, it was actually an exchange of photons that was creating an electric field that was keeping the balloons apart. Gravity, they've proposed, might be, and this is kind of clever, gravity might be carried by particles called gravitons. So what would happen with the gravitons is that I would let go of this ball and gravitons would make it fall. Problem is we've never been able to find them, and it sounds cool, but realistically it isn't like, oh, I'll put my hand in between and I'll block the gravitons, okay? No. So the warping of space and time, which we'll get into later, is an easier explanation. But so this is on my all-name team. So they think that the charge carriers for the strong nuclear force, because of like the glue that holds the nucleus together, are called gluons. Okay, so the strong nuclear force is held together with particles that holds the protons together, are particles called gluons. So, but without those gluons, again, we wouldn't be here having this discussion. So if the universe only existed with gravity and the electromagnetic force, we wouldn't be here, because you would never be able to form a nucleus, okay? Because the protons would never be stick together. You wouldn't have helium, you wouldn't have carbon, you wouldn't have nitrogen. We would never have DNA, you would never have iron, you would never have anything beyond hydrogen. So because of the existence of the strong nuclear force, That's what allows us to be here having this discussion. So, the only thing I'm going to expect you to know about the strong nuclear force is the strongest force, but it acts over the shortest distance. Now, the weak nuclear force, just to briefly mention this, weak nuclear force is important, but without it, we wouldn't be here having this discussion, because without the weak nuclear force, you wouldn't have the fusion process that takes hydrogen that's happening in our sun right now, where hydrogen combines to make helium, and then you get energy, and that's how we get light and all this other stuff. So, the weak nuclear force, I promise you, if I ever ask you something about 4 fundamental forces, the answer is never going to be the weak nuclear force. Okay? So if it's like a multiple choice, do not pick the weak nuclear force. It is not the correct answer. Okay? It's not it. Do not ever pick the weak nuclear force. Okay? Don't. It's not there. Now, we'll get into a little bit towards the end of the class, once we get into like radioactive decay and things like that. But for now, don't worry about the weak nuclear force. So, there was a brief glimmer of hope amongst the physics community. And again, you have to understand, all the people doing this research were physicists. So they said, oh, and they'd all studied, Newtonian physics. They had all studied gravity. And they said, they were very excited at this point. Because they said, the nucleus will be like the sun. And the electrons moving around the nucleus will be like planets moving around our sun. Okay? They said, this is cool. We can model this. So they began then to think of the atom as like a really, really, really tiny solar system, where instead of the sun, you had the nucleus. Instead of planets, you had electrons. And this is why, if you look at like your typical model of the atom, it'll have a dot, okay? It's the nucleus. Then it'll have circles going around it, because that's what it fit their mindset. I said, this is cool. It's like a little nucleus. And they'd all studied gravity, and they all knew this. But here's the problem. It didn't work. It's a train wreck. Because here's the reason why. So let's say, for example, I swing this rubber stopper around over my head, right? Okay? Over a period of time, I'm going to get tired, right? And this thing is going to slow down, and it's going to collapse. So that's what would happen if you had a very simple model of electrons. We'll get more into this later. But when things move in a circle, they accelerate, because they're moving in a circle, because they're changing the direction of their velocity vectors. And so what should happen is that when these electrons are accelerating, they should emit energy in the form of radiation. And they should all collapse and fall into the nucleus. But obviously they don't, okay? It's still a table, okay? I want to walk in Monday morning, probably still a table. So if the electrons all collapsed into the nucleus, then we wouldn't be here, because you wouldn't have stable atoms. So it's like, well, that model was cool and it was simple, but it doesn't work. So we'll get more into this in the spring. But they came up with what's called the wave function, where electrons actually travel in waves, and that's why they can't collapse, and you get into what's called Schrodinger's equations, which are probability equations to describe where the electrons are. So and you'll hear me say this again, I'm just going to plant the seed now. What happens on an atomic level is so incredibly weird, that don't think about it, okay? Do not think about it. If you want to read a great book on it, if you want a good book, there's a book called The Dancing Woolly Masters. Okay, it's one of the great reads on, and it's cool because it ties together like quantum mechanics and ancient Chinese philosophy. So if you ever want, like, it's not a heavy read. They don't get too far into the math, but it's a great book. It's called The Dancing Woolly Masters. And so if you want kind of a philosophical approach to the atomic world, that's a good place to be. Okay. So I'm just saying, if you're all interested in it, if you're looking, mom and dad, hey, what can I get you for Christmas? Get The Dancing Woolly Masters. It's a good book. Okay. Might even probably get it on books on tape or listen to it, things like that. Okay, so here's where we're at. So we've got 4 fundamental forces, right? Now, the manifestation of those forces plays out in your life. The 2 that are going to be most important is the electromagnetic force, and gravity. Okay? Obviously, the strong nuclear force is important. If we lose the strong nuclear force, we're all screwed because all of our protons are going to go flying apart and bad things are going to happen. Okay? But it's not going to interact with your day-to-day forces. Okay. So here's what we're going to begin to do. We're going to begin to look at Newton's 3 laws of motion. And these are on the back of those lecture notes. And I'm never going to ask you, like, what's Newton's first law of motion, okay? In terms of, like, being able to memorize that. You just need to understand the conceptual part of it. So the first law is what's known as the law of inertia. So, and this is, it sounds simple, but it's actually fairly complicated. So when you talk about inertia, okay, let me explain what inertia is not, okay? Inertia is not a force, right? The only thing, and listen to me and hear me out right from the beginning. The only thing that determines the inertia of an object is one thing and one thing only. The amount of mass that it has, okay? It isn't where you are in the universe, it isn't whether it's Friday, it isn't whether it's windy outside, relative humidity, gravitational field, doesn't matter, okay? There's only one thing that determines the inertia of an object, and that's mass. So here's the classic example. So here we have Hank the bowling ball, right? And we have Gary the golf ball. Which one's going to be easier to speed up and slow down? Gary is, right? Because Gary doesn't have as much stuff, right? So inertia basically is a reflection of the amount of stuff that you have inside the object. So if I look at Gary the golf ball, okay, and I look at Hank, okay, they're both made up of protons, electrons, and neutrons. There's just a lot more stuff that makes up Hank than there is that makes up Gary. Now, you'll hear me say this again and again and again and again and again. Mother Nature is a lazy prima donna, which means Mother Nature is only going to do what is easiest for Mother Nature to do. That's it, okay? That's it. So, if Hank is sitting here, Mother Nature basically says, it's cool, okay? Mother Nature is all chilled. I envision Mother Nature as being like this gray-haired, you know, tie-dye, smoking on a hookah pipe, chilling out on the weekends kind of girl wearing Birkenstocks, right? And she's just like, dude, whatever, you know, I don't care. Here, have some hookah, you know? She's chill. And so Mother Nature sees Hank the bowling ball sitting here, and he's at rest, and Mother Nature goes, stay there, I don't care. And Mother Nature goes, if you want to make Hank accelerate, you got to apply a force to it. Okay, that's cool. Same thing with Gary. Gary's going to sit there. He's up. Gary's going to sit there until what?
You apply force.
Until I apply force to it. Gary's just going to chill out there. Now, listen to me very carefully. Here's the other side of the coin. Is that if I get Gary moving, guess what? Mother Nature says, if you give Gary a velocity vector, guess what? Mother Nature is going to keep that velocity vector until an outside force acts upon it. Now, listen to me very carefully. A velocity vector, what are the two things that make up any vector quantity?
Speed and a direction.
Well, well, that's going to be speed. But generally, it's magnitude and direction. Okay, those are the two things that are going to make up any vector quantity. So if I throw this ball and I give it a certain velocity vector pointing in this direction, parallel with the ground, Mother Nature is going to keep that. So if I see that change, okay, so when I throw this against the wall, okay, right? Oh. Okay, didn't break anything. All right, so let's try it over here. So when I throw that and I see that travel in a curved path, guess what? There has to be a force acting on it. Because if I let go of this and there's not an external force, what's Gary the golf ball going to do?
Keep going in the same direction.
Yeah, it's just going to travel in a straight path. So it's going to maintain that velocity vector. So the other thing we'll talk about, and that's the Jedi over there, the Jedi stove block, was to stop the force and watch. So if I stop applying a force with my hands and I watch what happens, oh, it begins to accelerate. Oh, that means there has to be a force acting on it. So, here's the first law of inertia, okay? Is that whatever motion an object has, whatever velocity vector it has, it will maintain that velocity vector until an outside force acts upon it, okay? So when you see something traveling in a curved path, you see something speeding up, you see something slowing down, Mother Nature goes, okay, hey, there has to be a force acting on it. Because Mother Nature by herself is not going to speed anything up, slow anything down, or make it travel in a curved path. There must be an external force that's causing that to happen, okay? So keep that in mind. Now, this is in contrast to Aristotle, okay? So Aristotle was one of the great Greek philosophers, okay? There's three of them. There's Socrates taught Plato, Plato taught Aristotle. Okay, so Aristotle was kind of the end of the line of these great Greek philosophers. If you can ever go back in time, go be a Greek philosopher. It's a sweet gig, okay? You lay around, you're in a toga, you really don't have to work, you just have to wake up every morning and find other Greek philosophers and you argue about things, okay? That's it. It's a sweet gig, okay? There's no quotas, there's no papers to grade, you know, there's no customer service, you just have to sit around and be a Greek philosopher. It's a sweet gig. Okay, so, but here's where things were changed based upon Aristotle. So Aristotle was a believer in something called natural states. So if I take this block of wood and I push it, what's going to happen? Every time. But as soon as I stop pushing it, what's it going to do? It's going to stop, right? Every time, okay? I said, okay, here's our lab today, class, right? We're going to push a block and observe what's going to happen. That's going to be fun, okay? Because every time, what's going to happen? Stop, right? If I drop this golf ball, okay, every time, what's the golf ball eventually going to do? It's going to stop. It's going to happen, right? Now, it would be cool if I had like the magic bouncing golf ball and I could drop that and it would bounce back up to the same height every time, okay? And I could just drop this and then I could like walk away and give my lecture and this golf ball is continuously bouncing back to the same height. That would be cool. You all would completely lose track of what I'm saying because you will be mesmerized by the bouncing golf ball. But it's a cool idea. So based upon our normal everyday existence, if you push something, what does it do? It comes to a stop. Your car runs out of gas. What's your car going to do? Come to a stop, right? Okay? So what's going to happen? So Aristotle goes, I see a pattern forming here. Things come to a rest. Now, if I want to keep the block moving, what do I have to do?
Keep pushing it.
I have to keep applying the force, right? Because this goes back to the Jedi-Stofa law thing. If I stop applying the force and watch, what does the block do? It comes to a stop every time, right? So if I stop pushing it and it accelerates, that means there's an external force acting on it. So it's somewhat analogous to you guys. We'll go to Eli, for example, in the morning. Okay, so tomorrow morning, 4 o'clock morning. What's your natural state of motion going to be at 4 o'clock on a Saturday morning?
Obviously.
At rest, right?
Yeah.
Okay, at rest. That's going to be his natural. It's for all of you. It's like 4 o'clock on a Saturday morning. Okay, you're out. Okay, that's it. Now, let's make it more realistic. Let's say it's 6 o'clock on a Saturday morning. Okay, and Adam's mom knocks on the door and says, "Hey, Adam, right? Aunt Martha's coming over for breakfast and the house is a disaster. And I don't want Aunt Martha gossiping about this house on Facebook, okay? So I need you to help me clean." And Adam's going, it's 6 o'clock on a Saturday morning, right? So that's his natural state of motion. So Mom is going to have to keep applying the force to Adam to keep him moving because his natural state of motion is to be at rest. So he's up and he's vacuuming, he's like, say half asleep doing this, right? He's like rubs a hole in the carpet because he goes over the same place like 10 times because he's falling asleep. But so then mom says, hey, I gotta go get a strudel at Dillon's, okay? And so she leaves, right? And she stops applying the force. Adam's gonna do this. Oh, he's gonna sit on the couch like, oh, right? He's gonna go back to his natural state of motion, okay? Because that's 6 o'clock in the morning, that's a natural state of motion of a teenager. So the same thing happens here. And Aristotle goes, look, the natural state of motion is for things to come to rest. And that was cool for about 2,000 years. So literally from about 400 BC until about 1600. Okay? For about 2,000 years, that was the accepted idea. So Galileo comes along, and he goes, and began to question some things. So the beauty of what Galileo did is that he imagined like a frictionless surface. Okay? And the beauty of what Galileo did is that he took the ideas and he took it one step further because he came up with these like thought experiments. He says, okay, if I take this ball, for example, and I give it a push, that is going to roll a lot farther than the block does. Okay, because if I push the block pretty much comes to a stop. But I give the ball rolls a lot farther. So why does the ball roll so much further than the block does? What's the difference?
Like more surface area on the table.
There's the surface area, which is going to create more
Friction.
friction, okay? Because friction is going to make this thing stop. So what Galileo did is says, what if we eliminate friction and I give it a push? So imagine this is the magic frictionless block, okay? It's a magic frictionless block. And if that's the magic frictionless block and I push it, what's the block going to do?
Not stop.
It's not going to stop, okay? It's just going to keep going. So what Galileo realized, like, look, the only reason things come to a stop isn't because that's their preferred state. They come to a stop because there is friction. If you eliminate friction, guess what? It's going to keep going. So then Newton took that and he rolled that into his first law of motion. So Newton's first law of motion basically says objects at rest, and there's variations on this theme, okay? But one version is objects at rest remain at rest, or objects in motion, and the motion part is important. With the motion part, it's not explicitly stated, but there's two parts to that motion part. There's the speed part, and there's the direction part. So if I could, and this would be cool, okay? This would be the ultimate thing to have in the physics room. So imagine that I could push this, and then I've got a gravity switch, okay? And I'm going to turn off gravity in the room for just a second. So if I gave this push towards Christian, and I shut off gravity right as I let go of it, this block would go in a straight line towards Christian, okay? It wouldn't fall, because there would be no external force acting on it, and there would be no friction. So this would be like the perfect example of something, if I could push this and immediately turn off gravity, it would go in a straight line towards Christian because there would be no external forces acting on it. So in the course of this lab, okay, one of the main things, especially when we begin to study friction, is that what you have to understand is that the only reason you have to apply a force to keep something moving is because there is friction. If you eliminate friction, things will keep moving, okay? So when we're doing these calculations with friction, you keep this in mind. The only reason you have to apply a force to keep something moving is because of friction. You get rid of the friction, you don't have to apply the force because inertia will keep it moving, okay? So, stop that camera for a second. Okay, so here's Newton's first law. And this is why you can't look at one law in isolation. You have to look at all three laws at the same time. So the first law is law of inertia. It says objects at rest remain at rest. Now, this is where you already understand the first law. So here you have Hank, right? And here you have Gary. They both have mass. They both have inertia, okay? But Gary doesn't have as much mass. So even though he does want to move in a straight line, because of the fact there isn't as much stuff moving in a straight line, it's easier to slow that down, okay? Hank has a lot more stuff. So it's harder to get Hank to move, but once you get Hank moving, guess what? It's hard to stop him. So don't take Hank out to the golf course and try and hit your driver on Hank, okay? Bad things are going to happen, right? Because Hank has a lot of mass and the driver's going to hit and the driver's going to go, okay? Just shatter. Hit Gary the golf ball, hey, you can hit Gary the golf ball 250 yards. You're not going to hit Hank 250 yards. But don't go to the bowling alley and go, oh, we'll take Gary the golf ball, we'll go bowling with Gary, okay? Which would be cool because you could roll Gary down the pins, or down the alley, and it's going to hit the pins, and it's not going to knock over the pins. So both have their applications for sports, but they're not interchangeable. And it's basically because it's a function of mass, and it's a function of inertia. So if I take, and here's the other thing that's going to be important. If I take both of them to the moon, okay, they're both going to have the exact same inertia as they do right here. So if I'm on the moon and I try and move Gary back and forth like this, if I'm on the moon, I'm going to have the exact same experience moving him back and forth horizontally. Now, vertically is something completely different. Weight is based upon your gravitational field. So if I'm on the moon, it's going to be easier to lift Gary vertically because I don't have as much gravity to overcome. But in terms of like horizontal motion, there would be no difference in horizontal motion on the Earth versus on the moon versus on the International Space Station versus in the middle of deep, 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 deep space. Okay? So your inertia never changes because it's based upon mass. Weight does. Now, let's talk about F equals ma. And this is also going to be the basis of the lab that you're going to do today, or start today. So here's the deal. One of the things you have to begin to differentiate is the difference between just saying a force is acting on an object versus what we call a net force. And we'll spend an entire day talking about net forces. So today I'm just kind of planting the seed. So here I've got this block of wood. So there's a couple of ways that I can figure out how much this block weighs. If I knew its mass, so let's say that I know that the mass is 0.5 kilograms, okay? Just to make up the number. So if I multiply that by 9.8 meters per second squared, okay? And I'm just going to use Fg equals mg, I would get 4.9 newtons. So if you know the mass of any object in kilograms, and you're going to have this for the lab, okay? If you know the mass of anything in kilograms, and you want to know what it weighs, just take that number, multiply it by 9.8 meters per second squared. Now, don't get hung up on, ooh, do I make it positive? Do I make it negative? Ooh, I don't know. Just get the number. Then decide in the context of the problem, does it make sense to make it positive or negative, okay? But again, listen to me. When I talk about what something weighs, I'm talking about a force that's in newtons. If I want mass, that's going to be in kilograms, okay? So unless I specifically say, hey, what's the mass of an object? That's going to be in kilograms. If I talk about weight, a gravitational force, something like that, that's going to be in newtons. Now, here's the other thing that I can do. So here I've got these digital Newton scales, okay? And you're going to use these a lot. So I want to make sure everybody's cool with how these work. So hopefully you don't struggle with the on-off button, okay? Now, these actually have to be calibrated back to 0 depending upon how you're going to use them. So like, I'm going to lift this block up. So if I hold this scale horizontally, it reads 0. But if I'm going to hold that block up, I'm going to turn it. Now, when I turn it, the scale actually goes to 0.06, okay? Because at this point, I've got to recalibrate the scale, which isn't any big deal, okay? And to re-zero it, all you have to do is hit that on-off button. You hit that button, once it's in the position that you're going to use it, and that reading should go back to 0. Because if you don't, you're already starting off like 0.06 newtons, and that's not what you want. So they're really cool. There's no springs. It's a great measuring devices, okay? But you just make sure that you recalibrate them. So here's the simplest way to figure out what something weighs. Just take this, hook it up, and like I get 3.93 newtons, okay? So and it's kind of cool if you think about it on a larger scale. So every proton, electron, and neutron that makes up this block of wood is attracted to every proton, electron, and neutron that makes up the Earth, okay? And the sum total of all those attractions between all those individual particles adds up to 3.93 newtons. So when this block is sitting here on that table, okay, what we've got is, here's this block of wood. So we have a gravitational force acting down, and I'm going to make that negative. And then we have an upward force, which we're going to call Fn, and that stands for force normal. And no, there's not like an abnormal force. Okay? All right? Now, let me explain how you technically calculate force normal. And later on, you'll see where this comes from. For now, just accept it. Okay? So force normal technically equals the gravitational force times the cosine of the angle. Okay? Technically, that's how you calculate your force normal. But here's the deal. For those of you that have studied trig, which is, I'm guessing, the vast majority of you, right now we're on a flat surface. What is the cosine of 0?
It's like 1.
1, right? Cosine of 0 is 1. So if you're on a flat surface, technically, you calculate your normal force, you take the 3.93 newtons times the cosine of 0 degrees. But the cosine of 0 degrees is 1, so we don't have to worry about it. Okay? So for now, okay, this isn't an always kind of thing. Okay? Eventually we're going to be on inclined planes. Okay? But for now, like for the lab today, you're on a flat surface. So you do not, for now, have to worry about the cosine of 0 degrees. Now, if you're a purist, it's like, oh, Burkamp, I got to write that down. That's technically how I calculate it. If you really want to write down force normal equals 3.93 times the cosine of 0 degrees every time, knock yourself out. Okay? I'm happy for you. Okay? It's, you know, if you have to be really hardcore. So here's the important part. So right now, then my normal force is going to be a positive 3.93 newtons. So the reason that I made my gravitational force negative is because it's acting downward. And typically we're going to define things that act downward as being a negative value. So what the role of this table, what the table is doing through the electromagnetic force, because the electrons that make up this block of wood don't like the electrons that make up the table, right? And they're not merging. So it isn't like I lift this up and, oh, there's part of this block of wood that has stayed on the table. Or if I lift it up, there's a chunk of this table that goes with this, which would be really awkward, okay? They don't like each other. That's why I don't have to worry about that. So there's enough of a repulsion, and if you think about it, so gravity's trying to pull this block down, okay? The table is going, no, I got you, okay? I'm not going to let the gravity pull you down. So the electromagnetic force, which is acting upward, is keeping the gravitational force from pulling it down. Because if I pull the table away, what's going to happen? It's going to begin to accelerate, okay? Because gravity's still pulling it down. Now, at this situation, and this is why you have to talk about Newton's second law, which is force equals mass times acceleration, okay? And technically, I didn't have room to put it up there, but technically that is net force equals mass times acceleration. So it's only when you have an imbalanced force is when you have an acceleration. Now, listen to me. Just because a force is acting on an object doesn't mean that it accelerates, okay? So right now, Angelina's sitting back there in her nice purple shirt. Is that a K-State shirt or just purple? Oh, good. Okay, 10 out of 10. Okay, so she's sitting back there in this really cool K-State shirt, right? And she's sitting here in this chair, and like this, okay? And gravity is trying to pull her down, okay? So there's a force acting on Angelina. Angelina, are you accelerating? No, okay, she's not. And the reason being is because the chair is providing a normal force that's balancing out that pull of gravity. Now, we're not going to do this because she's wearing a K-State shirt. If she was wearing a KU shirt, I'd do this all day. But since she's wearing a K-State shirt, I'm not going to do this. But what if I went up behind her and I grabbed the chair and I pulled it out from underneath her? If she was wearing a KU shirt, I would actually do this, but she's not. So, what would happen if I did that? She would begin to accelerate, because then there would be an imbalanced force, okay? So, here's the beauty of all force problems, okay? Listen to me, listen to me, listen to me. At the end of the day, every force problem, there's only one of two things that can happen. Either all of the forces add up to equal to 0, and Angelina does not accelerate, or we shoot her out of the cannon, we pull out the chair, we do something, and the forces don't add up to equal to 0, and Angelina begins to accelerate. So literally, every force problem you are going to work can only play out one of two ways. Either all the forces add up to equal to 0, and you're at a constant velocity. Now, listen to me what I said. I did not say you were at rest, okay? I said you're at a constant velocity, okay? Don't think, oh, if all the forces add up equal to 0, you're at rest. That could happen, okay? That's what's happening to all of us right now. All of our forces add up to equal to 0, we're at rest. But we could also be in the carrot car, okay? So we could also be in the carrot car driving at a constant velocity of 20 meters per second going down the road. So if you're cruising, today when you go home after school, and your speedometer is staying the same at 40 miles an hour, whatever that is, there's a whole bunch of forces acting on your car. But all those forces are going to balance each other out. Okay? So let's look at this. This is something simple, but this is one of the most profound things that you have to understand about forces. So a lot of times what we will talk about is the sum of forces. Okay? Sigma meaning sum. So in this situation, with this block of wood sitting here, okay, right there, so we got it. So I have two forces acting on it. I have gravity and the normal force, okay? That's what I've got. So you can check my math, but if I take negative 3.93 newtons and add that to a positive 3.93 newtons, I'm going to get 0, okay? That's it. Now, if all the forces, let's start to formulate something, right? If all the forces add up to equal to 0, what do you know about the value of the acceleration?
It's nothing.
It's nothing, okay? So if all your forces add up to equal to 0, no matter how many there are, if all your forces add up to equal to 0, you don't accelerate, and you have a constant velocity. Okay, that's it. So if you see something moving at a constant velocity, and we're not saying there aren't forces acting on the system. We're just saying that all the forces add up to equal to 0. Okay? That's it. That's it. Now, so this is why when you look at F equals ma, that's why I need to clarify this. Just because you have a force acting on an object does not mean that it's going to accelerate. All of the protons that make up every atom inside your body, and there are probably 10 to the 24th, 25th atoms inside your body, okay? And every one of them has a nucleus. And every one of those nuclei is composed of a whole bunch of protons that don't like each other, okay? And all these protons want to go flying apart because they don't like each other because they have the same charge. But the protons are being held together by the strong nuclear force. So even within your body, there's a whole bunch of forces going on, okay? But they all balance each other out. So here's the first thing you want to get when you talk about forces. If something's at a constant velocity, all you have to do is make the forces add up equal to 0. And it's not something weird. I'm not asking you to add up to the square root of pi, okay? You just make all the forces add up equal to 0. Because literally, every force problem that I give you, I can only make it do one of two things. What can I do with every force problem? What are my only two options? I can either make you move at a constant velocity, or
Accelerate.
I make you accelerate. That's it. Those are the only two options that I have on every force problem that I write for you. That's it. It's either constant velocity or you have accelerated motion. There is nothing in between. And if something's at a constant velocity, make all the forces add up to 0. And if they're not accelerating, guess what? The forces don't add up to equal to 0. That's it. So if you look at Eli and his hacky sack, right? Eli, you have that hacky sack in front of you. Now put it back down. Right there. What are all the forces acting on that hacky sack? What do they add up to? 0. Now I want you to lift that up. Now when you were lifting it up, when you lifted it up, did you make it accelerate? Sure you did. Because if it was sitting on the table and you didn't make it accelerate, what would it do?
Oh, it would just stay there.
Yeah, so you made it accelerate. So when Eli was accelerating that hacky sack, guess what? What did all the forces not add up to? 0. Now you're holding it again. Is it accelerated? No. What do all the forces add up to? Now I want you to let go of it. As soon as he lets go of it, what does it begin to do? It accelerates. Oh, that's kind of cool, right? So when he lets go of it, what do all the forces not add up to? 0. Oh, it's falling. It's accelerating. What's the only force acting on it? Gravity. Oh, it causes an acceleration of 9.8 meters per second squared. Now it hits the table. Hits the table. Does the table make it accelerate?
Yes.
What if it bounces?
Yes. It makes it accelerate. How do you know the table makes it accelerate?
It stops.
It stops. The velocity changes. Guess what? When it hits the table, what do the forces don't add up to? 0. Now, right now, it's sitting there. Okay? Like hacky sacks do. What do all the forces add up to? 0. Literally, every problem start with that idea. Oh, it's constant velocity. Everything adds up to equal to 0. Oh, it accelerates. All the forces don't add up to equal to 0. That's it. Okay? If you think about all of the motion that you have experienced in your life, all of your motion can only be one of two things. It was either constant velocity or accelerated motion. Every moment that you have been on this earth, one of two things have happened. Either you've been at a constant velocity and all the forces have added up equal to 0, or you've accelerated and all the forces didn't add up. And you're going, oh, that's kind of cool, right, if you think about it. And it is. Okay, so this is why, when you look at Newton's second law of motion, this is why it's technically the net force, which is your imbalanced force, which is going to cause an acceleration. So the first thing I want you to get out of your minds is just because a force acts on an object does not mean that it accelerates. It only accelerates when there's an imbalanced force. Okay? Got that idea. Now, we're going to step it up a bit. We're going to step it up a notch. Okay? So let me get Hank out of the way here right quick. Stay. Okay? Now, I want you to listen to two words I'm going to say very carefully. I'm going to pull this block. Now, again, I'm going to pull the block horizontally. So now I'm going to re-zero it, because right now it's reading like negative 0.08. So now I'm going to pull this thing horizontally. So I'm going to hit that 0 button. Okay? And oddly enough, it starts reading 0 again. How cool is that? So now I want you to listen to two words I'm going to say very carefully. And those two words are constant velocity. Okay? So I'm going to pull this block at a constant velocity. So I'm at a constant velocity. What do I want all of the forces to add up to? 0, okay? Not pi, nothing weird, okay? So I'm going to pull this thing at a constant velocity, and it takes 0.94, close. Do that again. Takes about, actually 0.96. We'll call it 0.96. So here's the deal. So here's this block of wood, okay? We have gravity pulling down at negative 3.93 newtons. We have the normal force acting up, which is positive 3.93 newtons. Okay? That's kind of cool, right? Now, I've got this force pulling it. And we're going to call that the applied force, which is 0.96 newtons. Okay? Now, this is where this all comes full circle. Okay? What's the only reason I have to keep applying that force of 0.96 newtons to keep it moving?
Friction.
Evan.
Friction.
Friction. Because if this was the magic frictionless block, okay, if this was the magic frictionless block, and I gave it a push, what would it do?
Keep going.
It just keep going. So this is the most important thing that you have to get at this point. The only reason that that applied force of 0.96 newtons is there is because there's friction. Now, we're going to talk about two different types of mafia. Okay, I've kind of worked this in over the years. Okay, mafia. We have two types of mafia that we have to deal with. Okay, there's the frictional mafia, and then there's the gravitational mafia. Okay, so they're both trying to hold you down. Okay, so but they both require like tribute, like you have to pay them something to operate within this universe. Okay, because they're there. So here's the deal. Like I go to pull this block. The frictional mafia goes, oh, you're a good boy, huh? You want to pull your block? You're going to have to give me a little bit of money. You're a good boy, huh? Okay, it kind of gives a little love tap, like you're a good boy, right? So the frictional mafia has to be paid because it's there. If you don't pay the frictional mafia, bad things are going to happen. You're going to wear concrete shoes, okay? So the applied force is trying to keep this thing moving. The frictional mafia goes, you're a good boy. You got to pay me some money, huh? Okay? You don't pay me the money, you don't move the block. All right? So it's like this shakedown thing that has to happen. So I'm applying a force of 0.96 newtons. How much am I paying? How much do you think I'm paying the frictional mafia? How much is the frictional mafia demanding?
0.96 newtons.
0.96 newtons in the opposite direction, right? Because the frictional mafia isn't ever going to help you move. Your frictional mafia is always going to work against you, okay? It's like, frictional mafia is going, you want to move? Hey, fine. I'm going to work against you, okay? So, now I've got a frictional force going back this way of negative 0.96 newtons. Now, let's do a little bit of mental math, okay? Not just a Friday afternoon, okay? But I think we can handle this. So if I take positive 0.96 and add that to negative 0.96 and add that to positive 3.93 and add that to negative 3.93, check my math, but I get 0. Guess what? Is the block going to move?
Or it's not going to accelerate.
It's going to move, right? I just did. It's going to move, right? It's going to move. But is it going to accelerate?
No.
No, because all the forces add up to 0, okay? So when you see something moving at a constant velocity, assuming that the frictional mafia is there, whatever force you have to apply to move it is whatever the frictional force is that's acting in the opposite direction. So by measuring the applied force, we know what the frictional force is. Because the mafia, you know, they're not public, man. They're going, you know, we want to keep it low key. Yes?
If the applied force and the friction force were the same,
And they are.
like not be able to move it, shouldn't the applied force be a little bit more than the friction force?
We'll get to acceleration in just a second, okay? We're going to get to that part of the story, okay? But this is like after it's moving, okay? Because that's going to be I want to get to that, then we'll get back, circle around to that, okay? Hold that thought. So, if something's moving at a constant velocity, okay? I'm going to deal with that situation first. If something's moving at a constant velocity, all the forces add up to 0, okay? So, by measuring the applied force, my FAP, I know what my force is, right? I know what my frictional force is. So, this is my applied force, that's my opposing force. Sometimes it's called a frictional force. The generic way to put it is like, just call it an opposing force. If you like the mafia, call it the frictional mafia, okay? Whatever it is. I don't care how you think about it. Now, here's the deal. I pull the block along, okay, which I'm doing like this. Now, I'm pulling it along, and then I say, I'm tired. I stop pushing it. It's like, I'm 55 years old. I'm tired, okay? I've pushed that block God knows how many times across this table, okay, in my lifetime. I'm just tired, okay? So I stop pushing the block. When I stop pushing the block, what do I lose? Which of those 4 forces do I lose when I get tired and say, screw it, I'm done? I lose my applied force. But what's still there?
Friction.
Oh, the mafia is still there. The frictional mafia is going, hey, you know, you stop pushing? That's cool, right? We're still going to be here, right? So here's what changes. As soon as I stop the applied force, now what does everything add up to? Negative 0.96. Guess what? The forces at that point do not add up to, and you begin to accelerate. Oh, that's cool. Okay. Now, the frictional mafia brings it to a stop. Now everybody's just chilled out. Now what do all the forces add up to? 0. Now they add up to 0. Now, let's go back. Now I want to make it move. Okay? Now, I'm going to take my force sensor, and I'm going to pull a little bit harder. So like right now, I'm applying about 0.8 newtons of force. I'm applying a force to the block of 0.8 newtons. Why isn't the block moving?
I think it has to reach above 0.96.
Yeah, I have to overcome the friction that's holding it in place, okay? Because the frictional mafia is going, I like this block. I think we're going to hold this thing in place, okay? Just going to kind of chill out, right? You want to make it move, you've got to overcome the frictional mafia. So if I apply enough force, which I got up to about, I don't know, 1.2, right? So if I apply enough force to move it from rest, this is what we call static friction. There's kinetic friction, which is the friction of motion, and then you have static friction where things are being held in place. So static friction, the mafia is going, you're at rest, okay? You're a good boy. We want to keep you at rest. Now, so there's 2 things that you actually have to overcome to make something move when it's at rest. Inertia, because it wants to remain at rest, plus the frictional mafia is going, you're a good boy, we like you here, okay? So to make it move, you have to overcome both of those things. You have to overcome the inertia, which is a property of its mass, because it wants to remain at rest, and you have to overcome the friction. Now, but once you get it moving, what does the block actually want to do? It actually wants to keep moving, okay? It wants to keep moving because it's in motion, right? Now, if you could eliminate the frictional mafia and get it moving, it would just keep moving. So things stop because of the frictional mafia, okay? Good with that. Now, there's the 3rd law, okay? And the 3rd law sounds the simplest. Okay, the 3rd law says that for every force, there is an equal and opposite force, okay? All right? Sometimes it's said that forces are coupled, okay? Sometimes it says there's an action-reaction force, okay? This is manifested in different ways. And you would think this is the simplest law. Oh, for every force. Now, listen to me, okay? There's a key word to this. It says for every force, not 80% of the time, not 90% of the time, not half the time. Every force, there is an equal and opposite force. So for every action, there is a reaction, okay? Every, okay? Every. Not just on Fridays towards the end of the lecture, and this is what we're going to tell Burkamp so he doesn't go ballistic and make us stay after class. Burkamp, okay, we get it. Every force, there's an equal and opposite force. So I push down on this table. What does the table do?
Push back.
It pushes back up with me, right? Okay, that's what's going to happen. I hit Gary the golf ball with my finger. What does Gary the golf ball do? Gary pushes back with me with an equal and opposite force, okay? Now, every one. So but here's where this gets confusing. I let go of that block of wood. Why does the block of wood accelerate?
Gravity.
Gravity is pulling it down. So here's we're going to look at kind of some different scenarios. I got this block of wood. Clearly, gravity is pulling it down, right? Okay. So the Earth is pulling down on the block of wood. But by Newton's third law, what else is happening?
The earth is being pulled towards the block of wood.
What'd you say?
The earth is being pulled towards the block
Yeah.
of wood.
The block of wood is pulling up on the Earth. It's Newton's third law. Okay. Every action, there is a reaction. So when I let go of this block of wood, if for every action there is a reaction, why doesn't, which would be kind of scary, why doesn't the Earth start to move up towards the block of wood like the block of wood starts to move towards the Earth? Because what's Newton's first law?
Inertia.
Law of inertia. What has more mass, the block of wood or the Earth? The Earth. The Earth has a lot more mass, right? So this is where you have to look at all three laws at the same time. I let go of this block of wood. The block of wood has a relatively small mass. So guess what? It's going to have a big acceleration. Now, the Earth has a large mass, right? It has a large mass. So what do you know about the acceleration of the Earth?
It's gonna be like a dot.
It's going to be real small. Okay? So technically, when I let go of this block of wood, the Earth accelerated. Okay? Is it enough that we're going to notice it? No, thank God. Okay? So even if in my old age, if I jump up, I exert a force on the Earth. Guess what? The Earth exerts an equal and opposite force on me. Now, I accelerate, and thank God it isn't like, oh, Burkamp's going to jump, everybody hold on, because the Earth is going to accelerate out from underneath me. Okay? Which would be cool, don't get me wrong. But that's not what happens. All right, so we got through this. We'll just crank on the lab on Monday. Okay? So you've got a good weekend. You've got nothing to worry about. But we'll hit it hard on Monday. So stop that.